Hello and welcome back. The last time we talked about the differentiation and we talked about the variation part. We said that the f delta x equals the f x1 plus h negative fx1. So as this equation represents the variation for the function of fx, and as the delta x also equals h, as we mentioned that delta x equals x power 2 or x2 negative x1 equals h. So this function is called the VH. So the VH equals fx1 plus h fx1, and it's referred to as VH. V as is the function of variation. So VH equals fx1 plus h negative fx1. And we have also two other types of functions here for the variation. We have something called the AH, and it's the VH divided by h to show the average rate of change when h do not equal 0, of course, because if it equals 0 the definition will be undefined, so this result will be wrong. So this AH equals VH over H. And the last function here, we have the rate of change, not the average rate, the rate of change at a certain instant. It's called the instantaneous rate of change, but we refer to as a rate of change only is the limit of H approaches 0, VH over H. So every one of them includes the other. The AH includes the VH over H. The RH includes the limit of AH. So what does all this mean, or what is the use of all these functions? Actually, we can use them in something that we will say now. It apparently looks like physics, but we have here in math problems like this. If we have a metal lamina with a rectangular shape, and the width is twice the length, and the volume of this metal lamina, or the area of this metal lamina, increases so that it preserves the ratio between the width and the length, but it increases. So we want to find the area of this when the width equals 10 centimeters. We want to get the average or the rate of change. So we have a metal lamina, and its area increases gradually while preserving the ratios between the width and the length, and we want to get the rate of change and the area when the width equals 10 centimeters. So what we will do is first write the information that we had in our problem. We got the width equals double the length. So if we say that the width is 2x, the length equal x. And the area equals 2x by x to give 2x squared. So we will consider this as our function. So the fx equals 2x squared. Alright, this is the first point. The second point is to get the average rate of change. And we said that the average rate of change equals the variation function of x plus h negative the fx1 over the h. So as we have our function here equals 2x squared, we will substitute with x plus 1 in the first function and with x in the second function. So we have the average rate of change equals 2x1 plus h all to the power 2 negative 2x1 squared over h. So here we factorize this to get x1 squared positive 2x1h positive h squared negative 2x1 squared over h. So we distribute the 2 inside the brackets to get 2x1 squared plus 4x1 h positive h squared negative 2x1 squared over h. So apparently this one goes with this one to get for x1 h plus h squared over h. So we divide h by both terms here to get finally 4x1 positive h. So this is our final expression. Alright, what we needed in our problem is to get the area when the width is 10 centimeter. But we are stuck here with the edge. So before getting the area, we can get the rate of change. We said that the rate of change equals the limit of h approaching 0 and the average rate of change. And easily here the limit of h approaching 0 for x plus h, we substituted the h equals 0 here to get finally 4x, and substituting with x equals 10 as we had in our problem, the final result is 10 here. If the length equals 10, not the width, because the x here represents the length. So this is how we use the variation function when we want to obtain the value of something here, and the x we have it in a variable way. So we have x2 and x1. So easily we use the variation functions as we did now, and that was our lesson, and that's it for today. Thank you for watching, and see you next time.